Okay, this is the fifth Taylor polynomial example problem. Just like in the previous problems, we're given a function, and in this case, the function is natural log of 1 plus 2x. And the first thing we want to do is find the nth degree Taylor polynomial, so the third degree Taylor polynomial of this function centered at, in this case, 1. Once we have that, then we want to use Taylor's inequality to find the maximum possible error, so the error being the difference between what the Taylor polynomial gives us and what the actual function gives us, the maximum possible error if we can input any x value between 0.5 and 1.5. And then finally what we're going to do is we're going to plot the actual error value along this interval by plotting the absolute value of the difference between the function and the Taylor polynomial and compare the actual error to the error we calculated using Taylor's inequality. Okay, so let's start by getting the nth degree Taylor polynomial. So we want to get t sub 3 of x. And now remember, when it comes to Taylor polynomials, the subscript, the n, it's a little bit different than what we remember as far as like s sub n. It's the same concept. These are both partial sums, exact same concept. However, typically with s sub n, it was like, okay, if we plugged in n is equal to 3, it was like we were summing the first 3 terms. Usually that was the case, unless maybe the summation started at n is equal to 0, then if you had s sub 3, then that was like summing the first 4 terms. However, with the Taylor polynomial, yeah, it's still a partial sum. You're just summing a certain number of initial terms of the Taylor series. However, the n here is more associated with, you want to go up to the third degree, the nth degree. It doesn't matter how many terms you're summing. You want to sum every single non-zero term of the Taylor series until you get to the x minus the center point to the n power. In this case, that's cubed. All right, so to start, we go through the same process that we would do if we were building the actual Taylor series. And so to do that, we make 2 columns, and in the left column, we're going to put the function and its derivatives. So the function is natural log of 1 plus 2x. The first derivative is 1 over 1 plus 2x, and then times 2, so 2 over 1 plus 2x. Okay, f double prime is, let's see, so this is 2. So, okay, power rule, you get minus 2. Okay, then times the derivative of 1 plus 2x is just 2, so it's minus 4 over, let's see, so that's, okay, third derivative, we've got, so bring down the 2, that's positive 8, and then with the chain rule, we're going to get another 2, so it's going to be 16 times 1 plus 2x minus 2 minus 1 is minus 3. Okay, so now the third derivative is enough to get us to the third degree term, but we want to go at least one derivative more than that for Taylor's inequality. So the fourth derivative is, so 16 times minus 3 is minus 48, but then we're going to get a 2 from the chain rule. 48 times 2, that's 80 plus 16. That's 56, so minus 56. Okay, so 1 plus, okay, now in the right column, we want to plug the center point into each of these. So the center point is 1. Okay, this is natural log of 3. Okay, we've got, let's see, 2 over 3, so 2/3. Okay. Okay, 2 plus 1 is 3. 3 squared is 9, so minus 4/9. Okay. Let's see, 3 cubed is 27, so 16 over 27. And we can't reduce this anymore. So now the fourth derivative, we don't need to plug in the center point. The center point doesn't come into play with Taylor's inequality, right? Or at least plugging it in. We don't have to plug it in. So we'll just need the function itself. Okay, so we had f of 1. Okay, so now at this point, we don't need to be, when we were building the Taylor series, we're starting to look for a pattern. If we can't see a pattern here, then we actually we get the full C sub n coefficient and look for a pattern there. We're not looking for any pattern here because we're just taking the first 4 terms or the first terms, however many terms to get to the third order term. So all we need to do now is, so we know that C sub n is the nth derivative at the center point over n factorial. So this, what we have here, we've got the nth derivative at the center point. So now to get the C sub n's, we just divide by n factorial. So this is the 0th derivative. So natural log of 3 divided by 0 factorial is just natural log of 3. 2/3 divided by 1 factorial is just 2/3. Minus 4/9 divided by 2 factorial is going to be minus 2/9. And 16/27 divided by 3 factorial is going to be 16 divided by 2 is 8. So 8 over 81. Okay, so these are the coefficients on each of the, we're going to have 4 terms. So we can now put the Taylor polynomial together. So what we're doing is we're saying the function, natural log of 1 plus 2x, is approximately equal to this t sub 3. There's 4 terms, but this is t sub 3. Let me make some more room here. So yeah, there's 4 terms, but this is, we're going up to the x minus a cubed. So, okay, the first term is the coefficient times times x minus a to the 0. So it's just natural log of 3. Okay, plus we've got 2/3 times x minus the center point to the first power. Okay, then minus, we got 2/9, and then times x minus the center point to the second power, and then plus 8 over 81, and x minus the center point to the third power. And there it is. Okay, so now we want to use Taylor's inequality to get a ceiling on the maximum possible error we could get using the t sub 3 polynomial here to approximate the function value if we're restricting the x inputs to be along this range. Okay, so Taylor's inequality is going to give us the largest that the absolute value of r sub n can possibly be. Right, so R sub n it's just like what we learned about with partial sums in the first half of the chapter, but this applies with the Taylor polynomial and the Taylor series. So t, this is the function, right? So this is natural log of 1 plus 2x. That's the Taylor series, the infinite series, is equal to the nth partial sum, so the first whatever terms to get to the nth degree, and then plus everything else in the series past the nth degree term. Okay, we need an estimate on how big this could possibly, the largest this could possibly be. And we can start by getting the largest this could possibly be as a function of x, and then we can, once we have that, we can plug in the worst case scenario x to get an actual number. So no matter what x you plug in, you have an actual value that you know you can't be more off than. So, okay, but we've got t sub 3 of x. That's our Taylor polynomial. So we want to get r sub 3. So we're going to plug n is equal to 3 into Taylor's inequality. Okay, now this is what we're looking for right here. This is the upper bound on the r sub n. This is the inequality we want. And you can get this for all x values away from the center point, or for if you want some radius away from the center point. And that's actually what we're doing here. We're not thinking about all potential x values to answer this question. We're thinking about where the center is 1, we're plus or minus 0.5 from the center point. So we're looking at this with d equal to 0.5. Okay, so looking at this inequality, what do we need to get this inequality fully filled out? Well, we already have n. We already have a. Here's just an n. So the only thing we're missing is capital M. How do we get capital M? Well, we come up here. We need to look at the n plus 1th derivative of the function, the absolute value of that, analyze that over the interval we're interested in, plus or minus 0.5 from the center point, and see is there any value of the function over that interval to where there's a value that's greater than or equal to all other values, all other potential values of x that you can input. What does that mean? If you think back to chapter 4, we're finding what is the global max of this, the absolute value of the n plus 1th derivative over this interval. That's it. That's what m is, capital M. Okay, so what is the n plus 1th derivative, the absolute value of the n plus 1th derivative? Well, there you go. N is 3, so it's the 4th derivative. It's minus 56 over 1 plus 2x to the 4th power. Okay, so now what's the absolute value of this? Well, we can take away the minus sign, but then we can actually just take away the absolute value because even though x can be negative, 1 plus 2x to the 4th is always positive, so we just take away the absolute value. Okay, now we could go ahead and graph this in Desmos and just look at the interval from 0.5 to 1.5 and see what the max is, but we've done that with previous problems, but we don't need to do that here. I mean, what's going to make this the largest? That's when x is the smallest. So when x is 0.5, that's going to be the biggest value. So 2 times 0.5 is 1. 1 plus 1 is 2. 2 to the 4th is 16. 56 divided by 16 is 7/2. So this is less than or equal to 7/2 for all x. This is m for right. This here is just another way of saying this. So there we go. We have capital M. It's 7/2. Now we can just write out the inequality. Let's write this out. But we're going to do this with n equal to 3. So the absolute value of r sub 3 of x is less than or equal to, it was n plus 1 factorial, and then in the numerator was capital M, and then times the absolute value of x minus the center point to the n plus 1 power. Okay, so this is 4 factorial is 24. So let's see, 7 halves times 1 over 24. That's 7 over 48. Okay, so there we go. This is the upper bound on the error, the difference in between what we got with the Taylor polynomial at a certain value of x and the actual function. However, it's a function of x, though, here. So yeah, let me put that. This is a function of x. Specifically, only these x values. Okay, but we can go a step further. Let's just plug in, what's the worst case scenario x value here? Well, that's going to be when we're as far from the radius as possible in this situation. For the capital M, it could be the case that the capital M comes from some position within the interval. In this case, it was at the endpoint, one of the endpoints, but it might, for another case, you might get capital M for somewhere within the interval. But that doesn't mean you have to use that same midpoint here. This is totally independent from getting capital M. We're just saying, okay, what's the worst case scenario here? Once we calculate the M, we forget about the M, and we've gotten the formula for the R sub 3 of x. Okay, so now we're just asking the question, what's the worst case scenario? Well, that's going to be, for every time at this step, it's going to be the farthest away from the center point, which is going to be 0.5. So the absolute value of x minus 1 is going to be the largest when it's 0.5 away from the center point. So 0.5 to the 4th times 7 divided by 48. 0.00912. So there we go. No matter what x you plug in, as long as it's within the interval from 0.5 to 1.5, no matter what x you plug in, the error between the what you get with the Taylor polynomial and the actual function, the difference, will never be greater than this. Okay, I made a mistake here. I forgot to multiply this. We did 16 times 3, but I forgot to multiply by 2. Use the chain rule, multiply by 2. So, or I'm not sure what I did. So 16 times 3 is 48. 48 times 2 is 96. So this is going to be, okay, so this is 96. Okay, so now we plugged in 0.5. So 2 to the 4th is 16. So it's 96 divided by 16, which is 6. So capital M is 6. Okay, 6 divided by 24 is 6 times 4 is 24, so 1/4. Okay, now 0.5 to the 4th is this, and then divided by 4, so 0.0156. There we go. Okay, so now let's go ahead and graph the actual R sub 3 of x, absolute value. We can do that because what is R sub 3 of x? It's the absolute value of the function itself minus t sub 3. Okay, now you might ask, well, why didn't we just, what's the purpose of Taylor's inequality if we can get the actual exact error? This is just practice. In some cases, maybe you don't have the actual function, or maybe it's hard to get the actual error. So these problems are just we're practicing the mechanics of Taylor's inequality. Okay, so there's the absolute value of r sub 3 of x. Let's see, at the endpoints is where this is the largest. And it looks like this is the left endpoint. We're at about 0.0042-ish. Taylor's inequality, we got 0.0156, so not bad.